This is the first problem. We are asked to simplify this expression. So the first step is to combine the denominators. Here we see a plus, here we see a minus. And so we'll try to multiply the first term with this expression here in the denominator. And we multiply the second term with this expression here. So it looks like this. So we multiply this whole term, these two terms here with this, and these here with these and these. And now we have the same denominator, so we can combine them together. And the numerator, the subtraction sign goes to the numerator. And now they become like this. Now what we can do is factor out square root of 5. And in the denominator, we can use the difference of squares because they only differ by this sign, plus and minus here. So this will be the square of square root of 2, which is 2, and the square of 1, which is 1, and we subtract them. So it becomes like this. And the square root of 5 is factored out. So what remains inside is square root of 2 minus 1 minus, then we distribute the minus sign into square root of 2. So that's negative square root of 2 and minus 1. So minus 1. And again, this is from the denominator is obtained from the identity a plus b times a minus b equals a squared minus b squared. And now in the numerator, we can see that the square root of 2 here cancels with this bit here, and we are left with negative 1 minus 1. And so the numerator becomes negative square root of 5. In the denominator, or rather, negative 1 minus 1 is negative 2, so negative 2 square root of 5. And in the denominator, we are left with 2 minus 1, which is 1. So this is the final answer. We are asked to decompose this expression into partial fractions. Now the first step is to factor the denominator. These are the factors of the denominator here. Now each of the factors will become a denominator in the expansion. So x becomes a denominator here, x squared becomes a denominator here, and x plus 1 is also a denominator here. Now we notice that x squared is actually a repeated form of x, and the theorem states that if you have a linear denominator, then the numerator must be a constant. So the numerator of this term is the constant a. The numerator of this term is the constant c. Now, because x squared is just a repetition of x, and we have to write that because we have an x squared here, then the numerator of this is also a constant, just like the x here. The next step is to multiply out both sides by the denominator here. And so this is what we get. The denominator on the left side is removed because we multiply it by the term. And then here, each of the terms will be multiplied by this denominator. For example, when we multiply this term by this denominator, one of the x's here cancel with the x here, and so we are left with x times x plus 1. And the same is the case with these other terms. Now, our task is to maintain the identity with respect to x. What that means is that the coefficient on the left side must be the same as the coefficients on the right side. And so the first step after the decomposition here is to put this in a form that is very similar to the left side. So we multiply out everything, and this is what we get. So we have ax squared, and here we also have cx squared. So we group together. Next is we group together the ax squared and the cx squared. So we're basically grouping like terms. The same is true with the ax and the bx, and also the b. Now it becomes like this. Now we can compare the coefficients of the left and the right. So here we have 1 as the constant term, and here we have b as the constant term. Therefore, b equals 1. So that will go here. Now we can compare the coefficients of the x term. Here the coefficient is a plus b. Here the coefficient is 0. Therefore a plus b equals 0. And we already know b to be 1, so we substitute that here and we get a equals -1. We do the same thing for a plus c and 1 here. We have a plus c equals 1, and we already know a to be -1, and so we replace it here and we get c equals 2. And therefore we have the answers here. It's -1, 1, and 2. Now we are asked to compute x plus 1 over x and x squared plus 1 over x squared if x squared minus 5x plus 1 equals 0. The technique I use to solve these kinds of problems is to assume an answer here and then manipulate this equation to obtain this quadratic equation. So here, that's what we'll do. So we start with x plus 1 over x. Suppose the answer is a. We don't know yet, but we're looking for a. Now, if we multiply both sides by x, we get x squared plus 1 plus, or rather equals ax. Now, I want to make this look like the given. So I move the ax to the left side. And so we get ax squared minus ax, or rather x squared minus ax plus 1 equals 0. And now I compare that with the given. Now it's easy to see that a must be equal to 5. So we get a equals 5, and x plus 1 over x is therefore equal to 5. Now for this part of the problem, what I do is I multiply, or rather I square both sides of this equation here. So if we do that, we get a squaring of this here, and here it's just 5 squared, so it's 25, and we continue to do that. So we expand this perfect square here, we get x squared plus 2 times the first term, x, the second term, 1 over x, plus the square of the last term, 1 over x squared. So again, this first part is just the expansion of this perfect square here. Now on the right side, it's just 25. Now we simplify the left side. So x squared remains x squared. 2 times x times 1 over x is just 2. And here we have 1 over x squared. Now we are asked for x squared plus 1 over x squared. So we just have to put this 2 on the other side. And therefore, x squared plus 1 over x squared is 23. Problem 4 reads, when the function y equals x squared plus ax plus b takes the minimum value -1 at x equals -2, then a equals blank and b equals blank. Usually in these problems you will see a quadratic, or something that can be reduced into a quadratic. And usually it will involve either a minimum or a maximum. And the general technique for these problems is to convert this into a form that looks like a parabola with the vertex. So the standard form of a parabola. And this is the standard form of a parabola. And this parabola is opening upwards. So y equals x minus h squared plus k. And a parabola that is opening upwards would look like this. And therefore, it will always have a minimum. If it's opening downwards, it will have a maximum. So if the coefficient here is positive, like in our problem, then it has a minimum. Looks like this. If it were negative, it would have a maximum, and it would look like this. And so this parabola is the useful form that we need. And the minimum is just k. So if we can put it in this form, k is the minimum, and it is minimum at h, at x equals h. So that's what we'll do here. We will put this given into this form. So to do that, we first complete the square. So x squared plus ax are the first two terms of the perfect square. So we just need the third term. And we remember that the third term can be obtained by dividing the coefficient in the second term here by 2. So divide it by 2 and then square that. And so this is the third term. And because we added something here, we have to subtract it here so that we don't change the value of the right side. And again, the squaring of a binomial looks like this. So if you have x plus v, if you want to square it, then you have x squared plus 2vx plus v squared. And so the coefficient here, 2v, is actually 1/2 the square root of the last term. So that's what we used here. And if we continue, now this term here, these terms here can now be expressed as a perfect square like this. So x plus a over 2, the square root of the first term, the square root of the last term. And then the constant terms outside are just collected into one expression here. And therefore, if we compare it with this bit here, we know that h equals negative a over 2. And that's because originally we have x minus h in here. So this should be x minus negative a over 2. So h is a negative a over 2. And for k, we know that it is just this expression here. And we are told that the minimum value, meaning k is the minimum value, so is -1. So k equals -1. And we are told that this happens at x equals -2. And therefore, h equals -2, because this is what it means. And so we do the following, because it's minimum at x equals -2, which is h, because h is where the minimum happens. And we know that h is equal to negative a over 2. We can say that -2 here is equal to negative a over 2. And therefore, if we multiply both sides by -2, we get a equals 4. And we do something similar for b. So the minimum is at k. That's already given, we know that. And it says here that the minimum is -1, therefore k is -1. And we also know from here that k equals b minus a squared over 4. So we can also replace a squared with what we already know, which is 4 squared. So b minus 4 squared over 4 is just 4. And now this leftmost side of the equation can be compared with the rightmost side of the equation. So we obtain -1 equals b minus 4. And if we add 4 to both sides, we get b equals 3. Here we are asked to find the range of x that satisfies this inequality. When we are asked to find something like this, the first step is to find the domain of the functions that are involved. So for example, in this case, the domain of the logarithmic function is such that the x's should be greater than 0. So all of the arguments or the inputs to the logarithmic function must be greater than 0. So that is the first step that we do. We write that down. So in this case, x must be greater than 0. So here the x's must be greater than 0. That is from this first part. And if we write that down in the number line, we now know that the only possible values for x, the only possible range of x could only be greater than 0. So in this notation, there is a solid circle here, but that's only because I couldn't find a hollow circle. Think of it as a hollow circle because we're only interested in x greater than 0 and not equal to 0. So that's again from this first part here. X must be greater than 0 because it is in the logarithmic function. And the same is the case for the second bit here. Then we know that x plus 1 must now be greater than 0 because again, the logarithmic function can only take positive values. And so if we solve that for x, we get x must be greater than -1. So what we did there was just subtraction of 1 to both sides. And now we know that the only possible values will be greater than -1. And because for the first condition, we know that the values must also be greater than 0, then therefore these values in between are not part of the range that we're looking for, because all of the conditions must be satisfied, and the values that satisfy all these two conditions or both of these conditions are only the values greater than 0. And we also have a third condition that must be satisfied, and that is that this term here must again be greater than 0 or positive, because again it's in the logarithmic function. And so we have x minus 2 must be greater than 0. And if we solve that by adding 2 to both sides, we get x greater than 2. And if we draw that here, that is from here to infinity. And now we see that everything below 2 and below, so even this part of the graph that used to be part of the range that we thought, is now excluded. So now the only parts of the number line that can be an answer are the parts that are to the right of 2. So this bit here, all these bits here will not be included in the range anymore. And so it looks like this. So only this bit. So only this bit are possible inclusions. Now I redrew our number line so that the 2 is now here, because we now know that everything to the left of 2 is not part of our answer. Only those to the right of 2 are possible to be part of our answer. So we draw it this way. And now we will try to manipulate the given equation, or rather inequality, so that it is easier to visualize. And so the first step is to make sure that the bases are the same, because it's easier to visualize them that way. And we use the following identity. The identity that if you have log of p base q, this is equal to log of p, the p from here to here, over log of q. So the q here goes inside to the base b. And b doesn't even matter. Any value of b works as long as it's greater than 0 and it is not equal to 1. And p and q must also be greater than 0. And again, q cannot be equal to 1, because if it were 1, then this expression here would be 0, and this will be undefined. So these are the only restrictions for the values of p, q, and b. And in our problem, we know that x cannot be equal to 2, cannot be equal to -1, and cannot be equal to 0. And therefore, we already have written these conditions in this number line. So they're already included in this number line. So we don't have to worry about these exclusions. Now, we just write each term using this identity, and we will use, in this case, the base e. So this becomes log of x over log of 2. So x in the numerator, 2 in the denominator. Here we have x plus 1 in the numerator, 1/2 in the denominator. Here we have x minus 2 in the numerator, and then 2 in the denominator. So far, so good. Now we have this bit here, and we can actually convert this into log of 2, because we know that if you have log of 1 over y, this is equal to the negative log of y, because that's just log of 1 minus log of y, and log of 1 is 0. So 0 minus log of y is negative log of y. And therefore, the second term here becomes like this. Now, all the denominators are the same. It's log of 2. And log of 2 is a positive number. If we multiply all sides of the inequality by a positive number, the inequality is preserved. So if it's greater than, it remains greater than. So let's do that so that we get rid of log of 2. Now it becomes like this. We just get rid of log of 2. And now we have a minus symbol here. And we can combine this bit with this bit. We know that if it's a subtraction, that becomes a division. So if we put them into one log symbol, that becomes x, becomes the numerator. The term x plus 1, the expression x plus 1, because it has a minus here, becomes the denominator. So we combine these first two terms into this one term here. And on the right, nothing really happens. So now we have this. And now we just want to remove log. Now we can actually just remove log because we know that log is an increasing function. By increasing, we mean that if we increase the value inside the log, then the log of that value would also increase. So that's what we mean by increasing. You increase what's inside here, you increase the log of what's inside. So if a function has that property, then we can just remove the function in an inequality here. And so we can just remove the log. And so we get x over x plus 1, which is the thing here, and is greater than x minus 2, which is the thing here. Again, that's because we know that log of something is an increasing function. Now, we can multiply both sides by x plus 1. That's okay, but we have to be careful because if x plus 1 were a negative number, then this sign would flip. If it's a positive number, then we don't have to flip the sign. And so we can consider the two possibilities that x plus 1 is a positive number, meaning greater than 0, in which case we have x greater than negative 1, we just move the 1 to the other side, or the x plus 1 here is a negative number, which we write to be x plus 1 is less than 0. And in this case, if we move the 1 here, we get x equals, or rather x is less than negative 1. And now we know that x plus 1 must be greater than 0. And that's because we know that the x that we're looking for must be to the right of 2. And if we have this, that's to the left of negative 1. So it's way further here on the left. So we don't actually have to consider this anymore. This possibility is non-existent because we're only looking for x's that are greater than 2. And so we only need to consider this possibility here, the possibility that x plus 1 is greater than 0. And again, this is because x must be greater than 2. Now we are convinced that the only possibility is that x plus 1 must be a positive number. And so if it's a positive number, then we can multiply this bit by x plus 1. So we multiply both sides by x plus 1, and the inequality symbol does not flip. So when we do that, so here we are left with x, and on this side we get x minus 2 times x plus 1. And if we write this down, if we expand this, we get x squared minus x minus 2. And now if we move this x to the other side, we get 0 on this side, and on this other side we get x squared minus 2x minus 2. So now we only have to worry about this inequality. Now, to see better how this is working, it is good to factor this out, to factor this quadratic here. So because what this is saying is that 0 must be greater than this, or rather this whole term here must be a negative number, right? Because 0 greater than something, then that something must be a negative number. And so let's factor that out. So the factors of x squared minus 2x minus 2 can be obtained by actually getting the roots of this quadratic equation. And so the roots of this expression here is actually given by the quadratic formula. And the quadratic formula is x equals the negative of the coefficient of x. So in this case, it's -2 here. So negative of that plus minus the square root of, again, the coefficient of x, which is -2, and you square it, minus 4 times the coefficient of a, or rather the coefficient of x squared, which is 1, times the coefficient, or rather the constant term, which is -2. And then all over 2 times the coefficient of x squared. Now we just have to simplify this. So here negative of -2 becomes 2. And then we have here 4. -2 times -2 is just 4. And -4 times -2 is +8. And here we just have 2. Now 4 plus 8 is 12. And the square root of 12 is 2 square root of 3. And now we get this, and we can cancel the 2's to obtain 1 plus minus square root of 3. So these are the roots of x. And so using these, we can now factor this expression. So we just copy this, 0 greater than, and now we factor this. So one of the factors would be x minus 1 plus square root of 3, and the other factor is x minus 1 minus square root of 3. So these are the two factors. And what this is saying is that the product of these factors must be a negative number, because it says here 0 is greater than the product. So this must be a negative number. There are two possibilities for this to be a negative number. First possibility is that the first expression must be a positive number, and the other expression must be a negative number. So that's the first possibility. And the way we write that is that this expression is positive, meaning it's greater than 0, and the other expression is negative, meaning it is less than 0. And if we solve that for x, we get x, if we just move this to the right, we get x must be greater than 1 plus square root of 3. And this, we just move x, or rather we just move this to the right, we get x must be less than 1 minus square root of 3. Notice that x is less than 1 minus square root of 3 cannot be satisfied together with this one. Why? Because you notice that both of these must be satisfied, right? Because it should be plus and minus here. So both of this and this, both of them must be satisfied. And the problem here is that we have these two contradicting conditions. The first condition says that x must be greater than 1 plus square root of 3, which means it is to the right of 1 plus square root of 3. And the other condition says x must be less than 1 minus square root of 3. And 1 minus square root of 3 is actually a negative number, and x must be to the left of that negative number. So how will you satisfy both conditions that says that it must be to the left and it also must be to the right? So nothing, no number satisfies that condition, those conditions. And so we don't even have to think about this in the number line. It cannot be satisfied. The only other possibility is that if this were positive here, and here is the negative bit. Earlier we had positive, negative, now we do positive here, negative. And if we write that, it is written as this bit here must be less than 0, negative, and this bit here must be greater than 0, positive. If we solve for x there, we get x, we just move it to the right, x must be less than 1 plus square root of 3, and x must be greater than 1 minus square root of 3. So what this says is x must be to the right of this number. So it's from 1 minus square root of 3 to the right. And again, we're only interested, we already have eliminated all the other things that are less than 2. So it should only be to the right of 2. So this condition is fine because It just says to the right of this number, and certainly these things are to the right of that number. And this thing says that it must be to the left. So x must be less than 1 plus square root of 3. So x must be to the left of this number. And 1 plus square root of 3 is actually a little bit greater than 2, right? So it's about here because square root of 3 clearly is greater than 1, right? So it will be a little bit here. And it says that x must be to the left, right? X must be less than this. So it's only to the left. So actually it's only this bit. So it's only this bit that we're looking for. And therefore, what we're looking for is actually here must be 2, and here must be 1 plus square root of 3. For problem 6, we are given a regular octagon. From 8 vertices, how many diagonal lines can be drawn? So we will just count the number of diagonals. We start with a regular octagon. So this is how I draw it. And then we can start anywhere, but here we will start at this vertex here. And we will just draw the diagonals from this vertex. And of course, we cannot draw a diagonal to the sides directly beside, or to the points, the vertices directly beside this vertex. And so our diagonals would look like this. From this to this, here, 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 here. And again, no diagonal to this side. And for this first drawing, we have 1, 2, 3, 4, 5. And for the second diagonal, we just move counter, or rather clockwise. So for the second vertex, we start here. And again, we draw the diagonals and we get 1, 2, 3, 4, 5. So for these first two vertices, we get 5 plus 5 equals 10 diagonals. Now we just move to this vertex, and we notice that we do not have to draw diagonals to the points that we've already considered. So we will always end at this vertex here for when we consider the diagonals. So for example, if we start here, we only need to consider this, 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 and this. So again, we don't go back to the start. And now we only have 4. And then we do that for this bit, and we notice that we will just have to reduce by 1 every single time. And that accounts for a reduction in a vertex that we need to consider. So for example, if we start here, we get these 3 green diagonals. And again, we end here because we've already considered this, this, and this. So if we don't have to draw this to here again. And so we have 3 there. And so we can guess that from here, there will only be 2. From here to here. And the last one from here would be just 1 here. And now here, when we're back here, we don't have any diagonals left anymore because the only remaining vertices would be this vertex and this vertex. And we already said that the vertex beside the other vertex will not have a diagonal. So the last diagonal is just 1. That is from this to this. Now we just add them all together. 10 plus 4 plus 3 plus 2 plus 1. And we get 20. For problem 7, we are given the geometric progression a8b and the arithmetic progression ab minus 8. And we are asked to look for a and b such that a is greater than b. Now, to solve this problem, we need 2 equations because we have 2 unknowns, a and b. And the 2 equations must be independent. And the way we get those equations from this problem is to use the 2 independent conditions. The first independent condition is the geometric progression, and the other, the arithmetic progression here. So let's do that. First, let's just write down this condition here to remind ourselves. Then we start with the geometric progression. For the geometric progression, we know that the common ratio must not be 0, because if it were 0, it would be 0, a 0, 0. So that's not really helpful. So we can rule out 0 as a possibility. And if it's not 0, then we can have the following relationship. The geometric progression that is given, A8b, is the same as A and the second term A times R. So 8 must be A times R, and the third must be, we just multiply it again with R, so A times R is AR squared, and therefore B is equal to AR squared. And we just write that down again, 8 equals AR, B equals AR squared. And now we have to remove R because we're only interested in B and A. So the way we do that is we notice that here we can have R equals 8 over A. And so we replace the R here with that 8 over A. And so 8 over A squared, because that's R squared. And if we do that, we get 64 in the numerator. We get A squared in the denominator times A. We are left with A in the denominator. And let's just make this a little bit more beautiful, and we see AB equals 64. We do that by multiplying A to both sides. Now for the arithmetic progression, let's assume that the common difference is B. And now for this common difference, we can have the given arithmetic progression to be equal to A, which is the first term, and then we add a D, which is the second term. So A plus D is B. And we add another D. So A plus D is A plus 2D, and this must be negative 8. And we just write that down. B equals A plus D, and negative 8 equals A plus 2D. And again, we just want to remove D because we're only interested in A and B. So D equals B minus A, and that's just from this bit here. We just subtract A from both sides. We get this. Now we replace the D here with a D here. So we get minus 8 equals A plus 2, and the D is replaced with this one. And if we just simplify that a bit, we get minus 8, 2B, and here we have minus 2A, plus A is minus A, or rather, we can write it A, we move A to the other side, and we move A to the other side, A equals 2B plus 8. From the previous slide, we obtained the two equations that we need. So AB equals 64 and A equals 8 plus 2B. This first equation can also be written as A equals 64 over B. Now, we have to solve these for A and B. And the first equation is used here. So 64 equals A times B. And A is replaced with this one. So 8 plus 2B, and B is retained. Now let's continue by dividing both sides by 2. So this bit here becomes 32, and this bit becomes B times 2B divided by 2 is B, 4 divided by 2 is 4, and that becomes 32 equals B squared plus 4B. Now we notice that we can actually complete the square here very easily by adding 4. So let's do that. If we add 4 to both sides, we get this expression on this side and this expression on this side. And what we're trying to find is B. So if we continue, we get 36 on this side. We get B plus 2 on this side. Again, this is a perfect square. That's why we get this B plus 2. And now we can just get the square root of both sides. So we get B plus 2, which is the square root of this side here, equals plus minus the square root of this is 6. Now we can just move 2 to the other side. So we get negative 2 plus or minus 6. If we use negative 2 plus 6, we get 4. If we do negative 2 minus 6, we get minus 8. So that means we can have two possibilities, B equals 4 or B equals minus 8. So let's start with B equals 4. If B equals 4, then A, we use this, A equals 64 over 4, which is 16. The other possibility is if B equals minus 8, then A equals 64 divided by minus 8. And so A is equal to minus 8. However, we are told that A must be greater than B. But in this case, the second case is such that B is minus 8, A is minus 8, so B equals A. Therefore, we don't want this. We only want this because here we have 16, which is A, and B is 4, so 16 is greater than 4, so it satisfies this. And therefore, A equals 16 and B equals 4. Problem 8 asks, the radius of the inscribed circle of an equilateral triangle with a side length of 6 is blank. So let's consider an equilateral triangle. In an equilateral triangle, all three sides are equal, and also all three angles are equal. And because the sum of the sides of a triangle, or rather the sum of the angles in a triangle is 180 degrees, and if each angle is equal to the others, then we just divide 180 by 3 and we get 100, or rather just 60. So 60 here, 60 here, and 60 here. Also, in an equilateral triangle, we know that the median is the same as the altitude, which is also the same as the angle bisector. So here we drew a median. So a median is the line segment drawn from a vertex to the other side, such that the point on the other side is the midpoint of this side. So that's what a median means. And for an equilateral triangle, this median is the same as the altitude and the angle bisector. So a median, as we mentioned, would bisect this side. So because this is 6, then we have 3, 3. This is the median. Also, this median is the same as the altitude. The altitude is that line segment such that it is perpendicular to the opposite side. So this bit here is 90 degrees. This is also the angle bisector. So the angle bisector is that line segment that bisects this angle here. And if this is 60, because it's an equilateral triangle, then each of these would be 30. And also, if we draw the other medians, so this is one of the medians, the other medians could be drawn here and here. They all intersect at one point if it's an equilateral triangle. And that intersection is actually the center of the inscribed circle. So the inscribed circle is the circle that is tangent to all three sides of your triangle. And so this is the center. This is where the medians, the altitudes, the angle bisectors intersect, and this is also the center of your inscribed circle. Therefore, this length from here to here is your radius. And this angle here, because this is also an angle bisector, this will be 30 here. And now we have a special triangle, 30, 60, 90. And we know that if you have a 30, 60, 90 degree triangle, then the side beside the 30 degree triangle, 30 degree angle rather, this side is actually 3 square root of 3 times the side opposite it. And so to get the side opposite it, we just divide this by square root of 3. And so we obtain r equals square root of 3. For the 9th question, we are asked to find n, such that if we sum this expression from k equals 1 to k equals n, the sum is 7 over 8. Now, for these kinds of problems, I noticed that when you have something like this, we can actually decompose this into two terms, such that we will get a telescoping sum. So this is what I mean. First, let's decompose this into two terms. Let's use partial fractions. And so 1 over this is equal to a over the first factor plus b over the second factor. Again, if we recall for partial fractions, if the exponent here is 1, here is 1, then the numerator would have to be constants. So a and b here are constants. Now, if we multiply both sides by this denominator, then we obtain this. 1 equals a times k plus 1 plus b times k. And we have to obtain b and a. So if we substitute k equals negative 1 and k equals 0, we will get the values of a and b. So here we do k equals 0 first. So k equals 0, this will be 0 here, and here will be 0, and so we have a equals 1. Now we do k equals negative 1. If we do that, then this expression here goes to 0, and there and here it's negative 1. So negative b equals 1, therefore b equals negative 1. And now we can express this sum as follows. This bit here is actually 1 over k minus 1 over k plus 1. And this is a very good form for a sum. And that's because this is what we call a telescoping sum. If we write that down, so 7/8, it's just 7/8 here. This is just a given. And now we can write the given like this. So now we have this. And if you actually start to write down the terms in this sum, we see the following. So let's start with k equals 1. So 1 over 1 minus 1 over 1 plus 1, which is 2. Now if k equals 2, we have 1 over 2. 1 over 2 plus 1 equals 3. So 1/3. Now let's do 3. So 1 over 3 minus 1 over 3 plus 1, which is 1/4. So 1/3 minus 1/4. And if we do k equals n minus 1, then we have k, 1 over n minus 1 minus 1 over n. That's this. And k equals n would be 1 over n minus 1 over n plus 1. And notice that this is a very good form because now these terms, this term cancels with this one. This one also cancels with this one. 1/4 also cancels with the next, and so on. And in fact, this one also cancels with the term previous to it, and until this one also cancels with this one. Therefore, we are left with 1 minus, so just this term here, and this term, 1 minus 1 over n plus 1. And again, this is equal to 7/8 in the very beginning. Now, we just move this around. So we get 1 over n plus 1. We move 1 over n plus 1 to the other side, and 7/8 to this side. So that becomes 1 minus 7/8, which is just 1/8. Therefore, n plus 1 is just 8. And so n equals 7. Question 10 reads, when a differentiable function f of x satisfies the equation, this equation here, then f of x equals blank and a, which is the lower limit of integration here, is blank. So we need to find the function f of x and the constant here, a. The first thing we notice is that f of t here is inside an integration symbol, and we're looking for that f of t. So the inverse process of integration is differentiation, and this is given by the fundamental theorem of calculus. So let's recall the fundamental theorem of calculus. It says that if you have an integral like this, you have an integral, so this is the integral here. If you differentiate this integral with respect to the limit here, x, so d dx of the limit of the variable here, x, then you obtain the inner function here, which is f, and now the variable will be x, so f of x. So this is the fundamental theorem of calculus. That means to obtain f of x, we just differentiate this side and differentiate this side. And let's do that. So f of x now, from the fundamental theorem of calculus, we differentiate this, and this expression is equal to this, so we differentiate this. This is just 2x minus 2. So f of x is 2x minus 2. Now we will look for a. We start by integrating f of t, because now we know what is f of t. So here we just write the given. So this is the given from here, and here from here. But now we know what is f of t. It's just 2t minus 2. So because we found f of x, we can just replace x with t to get f of t. And now we have this, so let's do the integration here. The integral of 2t is just t squared, and the integral of 2 is 2t. And the limits from a to x is written this way. And now we just replace t with x, so x squared minus 2x for this bit, minus, we replace it with a, so a squared minus 2a. And now we see that this is equal to this. Write that down. So this came from the given, and this came from our integration. Now we can see that this first term here actually cancels with this, and the second term cancels with this, and we're left with the third term, 1 equals the negative of a squared minus 2a. Now if we multiply both sides by -1, then we get a -1 here, then we add -1 to both sides, we get 0 on this side, and on this side we get a squared minus 2a plus 1. Now that's a perfect square, so there's only one solution. And if we do it this way, we get a equals 1. Problem 2. A trapezoid on a plane satisfies AB equals 5, BC equals 6, CD equals 3, AC equals 4, and AB is parallel to CD. Let O denote the intersection of AC and BD. Fill in the following blanks with the correct numbers. The first question asks us for the cosine of this angle here. And we notice that we know this side, we know this side, and we know this side. That means we can use the cosine law. In the cosine law, C here and C here are opposite each other. So C is the angle here, and this small c is the line segment here. That's the length of this line segment. And A and B could be anywhere between this or this. And in our case, let's just say that cosine C is this angle. C is, of course, this length, which is 4. And let's choose A to be this bit here, which is we know to be 5. And B to be this bit here, which we know to be 6. And if we just plug in all these values in the cosine law, we get this expression. And so we can actually obtain cosine of C, which is 3/4. So we write that there. Now we need to find BD. So that is this side. And we notice that we are given this side and this side. Now let's just find this angle so that we can actually use the cosine law to find BD. So let's use the cosine law. And to find this angle, we notice that we have two parallel lines, CD and AB. And this angle here is actually corresponding to this angle here, and they are complementary. So to be more precise, this angle actually corresponds to the other angle here if we extend this parallel, or rather this transversal. This angle is equal to this angle. And because we have a line from here to here, the angle, this whole angle from here to here must be 180 degrees. And therefore, the remaining angle, which is the angle that we're looking for, is actually 180 minus the given angle, this angle, which is actually equal to this angle. So we can find cosine C. So if we define this to be cosine C here, then because we know that this angle C is actually 180 minus this angle here, okay, 180 minus this, which is equal to this, we can get the cosine of C to be cosine of 180 minus this angle. But we know that if you have this kind of expression inside the cosine function, you can just remove the 180 and replace it with a negative sign outside. And again, we can imagine that from the definition of cosine, which is in the unit circle. If you have the angle here, so if this is your angle, and you have 180 minus that angle, then because this is 180 here, so minus that angle will be around here. And cosine is just the x component of this unit radius. So this is the cosine in here, so it's positive. Now it's here, so that is negative when we do a 180 minus the angle. And so we already know cosine of ABC to be 3/4, so just replace that. So cosine of C is therefore negative 3/4. And now we just plug in all the values to this, or in this equation. And these are the values again. And so if we plug them all, we get C squared, and we can actually get the square root of that, which gives us 6 square root of 2. Now we need to find the area of this triangle here. And because we have 3 sides, we can actually use Heron's formula. But I'm not a fan of Heron's formula because we have to compute semi-perimeters and all that. So I'm preferring to actually use the 1/2 side times the sine of this angle here, because we already know the cosine of this angle here anyway. So to use that, again, what we're using is the relationship that area is equal to 1/2 one side times the other side and the sine of the angle. And let A be this side here, which is 5, and then this side is BC, which is 6. And okay, this is, we just put this here for completeness, so AC equals 4. Now the cosine of C, meaning the cosine of this angle, is 3/4. And we know the relationship between sine and cosine from the Pythagorean identity. That's sine squared plus cosine squared equals 1. And therefore, if we solve for sine squared, we get the sine squared of C equals 1 minus the square of this, which is 9/16, and that gives us 7/16. And then we can say that the square root of that, sine of C, is just square root of 7/4. Now we can just plug this in here, and we already have A and B. And when we do that, we get this value, 15 square root of 7, 4. Now we need to find the angle ACD, or rather the sine of that angle. And to do that, we will actually need the sine law. The sine law states that if you have a triangle such that the sides are called A, B, and C, and the angles opposite them are called capital A, B, and C, respectively, then this relationship holds. So this holds for any triangle. And now we notice that we know a lot of things about triangle ABC because we've done questions 1, 2, and 3. And we notice also that the angle that we're concerned with, this angle here, is equal to the angle here. That's because we have a transversal AC. And again, that's because AB is parallel with DC, and therefore the angle here is equal to the angle here. So that's from being a transversal. And for convenience, let's call our angle, this angle, let's call that angle theta. And of course, this will also be angle theta. And the sine B, now we can use the sine law because we have this side, we have this side, and we have the sine of this side. So we are just looking for the sine of this side. So in our notation, let's call that the sine B that we're looking for. So sine B is actually the sine of theta. So that's what we're looking for. And the B is the opposite side, so BC, which is known to be 6. And sine A, so sine A, let's call this sine A here. So that's the sine A from here. So let's just have that to be sine of ABC. And we already know that to be square root of 7/4, and that's from question 3. And then lastly, AC, which we already know to be 4. So we just plug in these values into the first two parts of the series of equalities here, and we can actually get the value for sine b. So let's do that. So here we just plugged in the values, and the unknown is only sine b, and we just manipulate that a bit, and we get 3/8 times square root of 7. Here we are asked for the ratios of areas. So we are getting the ratio of the area of this triangle to that of this triangle to that of this triangle to that of this triangle. And when we're talking about ratios in triangles, similarity is a very useful concept. Similarity means that the corresponding angles are equal, and the corresponding sides of those two triangles are proportional. So to check for similarity, we have something called AA, which is, as we mentioned earlier, something to do with the angles being equal, and SSS, which has something to do with the sides being proportional, and also SAS, which means that if you have two sides, corresponding sides that are proportional, and you also have an included angle, included meaning the angle between the two sides, and if you have that included angle to be equal the other included angle, then you also have similar triangles. And we will use that in this problem. We see that by AA, using this triangle is actually similar to this triangle. And that means we can say a lot of things about the proportionality of their sides. And the reason we think they are similar is because of AA. That means we know two angles to be equal. So this angle, for example, is equal to this angle. That's because they are vertical angles of two intersecting lines. And this angle has also been shown to be equal to this angle, again, because they are transversals, rather because AC is a transversal of these parallel lines here. So now we have two angles of your triangles that are equal, and therefore they are similar. Now, if they are similar, then we can make the following proportions. So if we know this angle to be A, then the corresponding, or rather if we know this side to be A, then the corresponding side in this triangle, which is this, is also A times some proportionality constant. Likewise, if this is B, then the corresponding side on this triangle, which is this side, would also be K times B. And if we know this side to be C, then this side, which is the corresponding side, would be the proportionality constant K times C. So these things we learn just from knowing that this triangle here is actually similar to the other triangle, this triangle. And if we know that, then we can actually find K. So notice that we already know B, right? B is 5 from here. And we also know CD, which is equal to KB in our notation. So CD is 3. So B, this is to this. KB is just equal to 1 is to K, and we already know that the first term is 5 and the second term is 3, and so we have this proportion. And if we solve for K, it's just the inner terms, multiply them equals the product of the outer terms, which is 3, and we can solve for K to be 3/5. Next, we also know that the angle of ABO can be computed by 1/2 times this side times this side times the sine of this angle here. That's what we have here. So we've used this formula for the area in the previous problems. And that's for this triangle. Now, what about for the next triangle, BCO? So let's use again the same formula. So we have 1/2 times one of the sides, so this side times this side, so that's Ka, times the sine of this side, or rather of this angle. But this angle is actually supplementary to the angle here, to the angle AOB, which we already used in the area of ABO here. So if they're supplementary, then That means this is 180 minus the angle here. That's why we have it here. And if you have 180 minus the angle, if you get the sine of that, it's just the same as the sine of the angle itself. Again, this will be clear if you draw the unit circle and convince yourself that actually sine is just the vertical component of your unit radius. And so we can compute the area to be k, that's the k there, times the area of ABO. And that's easily noticeable when you solve this. So 1/2 CKA sine of the angle here. And you will see that this is in fact the relationship between those two. And next, we look at this area here. And again, that's 1/2 times this side, which is KA, this side, which is KC. So we get 1/2 K squared AC. And again, the angle here, which is just equal to the angle AOB in here. So that's again sine of AOB. And we already know the value for 1/2 AC sine AOB. So we know the value of 1/2 AC sine AOB. We replace that with ABO. And this is what we get for the triangle CDO. So we just move the K squared outside. And lastly, for the last triangle here, we do the same thing. We get 1/2 times this side, which is A times KC. So if you multiply that all together, that's 1/2 KAC. And times sine of 180, again 180 minus the angle AOB. And we already mentioned that if you have 180 minus the angle, and if you get the sine of that, it's the same as the sine of just the angle. And so we are left with 1/2 KAC sine of the angle, which is very similar to this again, with an extra K. So we can write it like K times ABO. And now we can see that we can actually get the ratio of this to this to this to this. And that's just 1 is to K squared is to K. And we already know K to be 3/5. So that's 1 is to 3/5 is to 925 is to 3/5. But in the given, the second term is actually 15. So how do we make this 15? 3/5 here must be multiplied by 25. So if you multiply the second term by 25, you will get 15. And so we have to multiply everything by 25 to get 25 here, and here we get 15. Now we get 9 here, and here we get 15 again. And that's how we got these numbers. Now we are asked to find the scalar product of the vectors CD and CA. So let's recall that the scalar product can be computed by getting the product of the magnitudes of the given vectors. So the magnitude or the length of this times the length of this times the cosine of the angle between them. So angle ACD. And we already know the side lengths. So CD is given to be 3, CA is given to be 4. Now we just need to know the cosine of ACD. However, we know from problem 4 the sine of ACD. So let's use that. Because the sine of ACD and the cosine of ACD are related by the Pythagorean identity, and we covered that in a previous problem here, previous question, we can get the cosine to be the square root of 1 minus the sine squared. So we have the value for this already. And so we just replace the sine there with a given value, which is square root of 7 over 8. And so we obtain cosine of the angle to be 1/8. Now we just plug this in, this expression, and we obtain 3/2. Problem 3. On the plane xy, there is the straight line A, and the graph of the curve B, y equals x cubed minus 3x squared plus 6 plus 1, as shown in the lower figure. The straight line A is the tangent to the curve B that passes through the point 1, 2. Points A, B, and C are the intersections of the curve B and the x-axis. Point D is the point of tangency of the straight line A and the curve B. Point E is the intersection of the straight line A and the curve B. Find the coordinates of the points A, B, C, D, and E. Just from the drawing and from the problem, we immediately see some answers for some of the blanks. For example, here we have A, B, and C, which are the intersection with the x-axis. And therefore, their y component must be 0. So we can just write 0, 0, 0 here. That's the y coordinates. It's on the x-axis. And also for D, D is the point of tangency, and at the same time it is also on the y-axis here. And therefore its x component must be 0. And so we write that there. Let us now think about how to solve A, B, and C in here. We know that A, B, and C are the intersections with the x-axis. And if that is the case, that means that they make y 0. If you look at that, and that is what we also have there. And so we know that we can have the following: 0 equals this. And at the same time, we also know that because there are 3 intersections, there are 3 factors of this polynomial. And those factors, let's call them x minus r, x minus s, and x minus t. Again, the reason for the 3 factors is that the curve intersects the x-axis at 3 points. And also we can see that from the exponent of x here. So the degree of this polynomial is 3. That means it has 3 factors. And now the first thing that we can do is actually try some values. Let's say, what about x equals r equals 1? Does this make this equation 0? So if we replace this with 1 here, does it give us 0? Because if it gives us 0, that means that 1 here could be a value here, here, or here. And in this case, let's say that's here in r. And clearly, if we replace that, we actually get 0. And therefore, we can say that r could be 1, and x minus r, this bit here, which is x minus 1, is in fact a factor of this expression. Now that we have r, we just need to find s and t. And the way we do that is we divide both sides, because x minus r times x minus s times x minus t equals this. Now we can divide both sides by x minus r, and so on this side we will be left with this, and on this side we get this, and we replace r with its value, which is 1. And now we can do the long division here, and when we do that, what we obtain is the following. So if you do the division there, long division, you get this. That means the factors of this expression are x minus s and x minus t. So we need to factor this expression. And the way we do the factoring is we set this to 0 and use the quadratic formula. Because if we set this to 0, we see that each of the factors actually gives you the value that sets the whole product to 0. So yes, we need to set this to 0 and find x. So now we just need to apply the quadratic formula. And this is the quadratic formula. And what we did here, if we will just review very briefly, this coefficient of the second term of the x term here, this goes here and here. And this constant term goes here. And the coefficient of the first term, the x squared term, goes here and here. And the 4, the minus 4 here, and the minus sign here, the plus minus here, and the 2 here, they are all fixed in the quadratic formula. And so if we simplify this, we get this. So 4 plus 4 is just 8, so that becomes 2 square root of 2. And now the 2's here can cancel. And now we get two values. 1 plus square root of 2 and 1 minus square root of 2. And that's very nice because each of them corresponds to s and t. Now we have r, s, and t. And actually, the values of s and t are interchangeable because we got them from the quadratic formula. And the quadratic formula doesn't really care about the plus and the minus. It just says that it's there. And now the way we assign S, R, and T to A, B, and C is by ordering them, because we notice that A is the smallest, C is the largest. So let's order these three values. And we see that S is the smallest, and T the largest, and R the middle. Therefore, we have the following. A is S, B is R, and C is T. Next up, we're going to look for D. So this missing coordinate here. Let's call that missing number lowercase d. Now we know that d is contained in this curve, and therefore it will satisfy this equation. If we replace the x's here with 0 and the y here with d, we should get an equation. So let's do that. So here we did the replacement. Y is replaced with d, x is replaced with 0. And we see that that gives us d equals 1, which we just wrote here. And now we're left with only this letter E. And before we do that, and while we are at this value of d, let us actually try to find the equation of line A. So line A, the general equation of a line is y equals mx plus b, where m is the slope and b is the intersection with the y-axis. And we already know the intersection with the y-axis, and that is d here, and that is 1. And so we can replace the b here with 1. Again, for any line, b is the intersection with the y-axis. Now we just need to find m. Now we know that m being a tangent, d being the tangent point or point of tangency between the curve and the line, we know that m is the derivative of this curve at this very point y, or rather d. So let's differentiate y and then replace the variables with the coordinates of d. So let's do that. So here we get m to be the derivative of the curve y with respect to x, evaluated at x equals 0, because d here has x equals 0. So we replace the x's with 0. Now let's do dy dx first. That's pretty simple. 3x squared minus 6x plus 1. And now we just replace the x's with 0. 0, 0, so we get 1. And therefore, m equals 1. And again, m is the slope of your line. And therefore, your line is actually, if you replace this with 1, you get a line that is y equals x plus 1. And that is the equation of your line A. So finally, now we can find the coordinates of E. First, let us set those unknowns to be u and v. So u and v. Now, E is contained in the curve B, and therefore it should satisfy this equation. So let us replace the y's here with the v and the x's with u, and this is what we get. Now, E is also part of this equation, line A, and the equation of line A is this. So we can replace the y's here with v and the x's with u. And this is what we get. So we now have two equations and two unknowns, this equation and this equation. And let us remember that we're looking for u and v. We have v, u, v, u. So we have to solve these two equations. So again, we let E equals u and v. And these were the equations that we got from the previous slide. So if we continue solving them, what we can do now is actually replace this v here with a u plus 1 from here. So let's do that. So it becomes like this. U plus 1 equals whatever is on the right. And we notice that we can subtract u plus 1 from both sides. So u plus 1, so we subtract u, we subtract 1, and we are left with this. And we can factor out u squared, and now we know how to solve this. The solutions to this are the following: u equals 0 and u equals 3, right? But u equals 0 is already this bit here. Therefore, e must be u equals 3. So u must be equal to 3. And that's why we place e here with 3. And now that we have u, we use this equation and we replace u with 3. And therefore, we get a v which is equal to 4.